All right, today we're starting a new chapter, 10.1, and this chapter is all about probability, which some of you it's going to come really easy to, while others it might be a little bit more challenging. Okay, but those of you who enjoy probability, who this comes easy to, make sure you enjoy this chapter. It'll go fast for you. Okay, so today we're starting 10.1, counting principle and permutations. Now, first thing, with probability, there's a lot of different kinds of experiments that we can talk about. Those experiments could include tossing a coin, rolling a dice, tossing two coins, drawing cards, selecting days of the week. I mean, there's multiple types of experiments. And within each type of experiment, you'll have a sample space. And the sample space is your possibilities or your probabilities. So if you're tossing a coin, your sample space is you're either going to get heads or tails. If you're rolling a dice, just a traditional dice, your sample space is rolling a 1, 2, 3, 4, 5, or 6. If you're tossing two coins, you still have heads and tails, but you're tossing two coins. So you can either get a head and a head and a tails and a heads, or a tails and a tails. Okay, so if you notice there, by tossing two coins, that sample space increased in size. Now, talking about decks of cards, without going into detail, which we'll do later, there's 52 possible outcomes because there's 52 cards in a deck. Talking about days of a week, well, hopefully we all know we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So depending on what your experiment is, will drastically change your probabilities in your sample space. Now, the fundamental counting principle. If one event occurs in m ways and another event occurs in n ways, then the number of ways that both events can occur is m times n. So we're listing events. We have one event m, another event n, and I want to figure out how many ways can they both occur. You just multiply. Okay, this is your fundamental counting principle. Okay, this also extends to more than two events, so you can do this for m, n, and p. Okay, or you could put a fourth event or a fifth event, doesn't matter. Okay, but if we're trying to figure out multiple events happening, you just multiply. So our example for that is you have 12 shirts, 7 pairs of pants, and 3 pairs of shoes. How many different combinations of outfits can you possibly have? Well, I have 12 shirts, 7 pants, and 3 shoes. All you do is take those and multiply. Different combinations. What are my options? Multiply your options. So 12 times 7 times 3, there's 252 different options or different combinations. Okay, you can say options, combinations, doesn't matter right now. There's 252 different options. So when you wonder why girls take so long to get ready in the morning, that's why. They have lots and lots of options of what to wear. Now, using the same rule, but now talking about zip codes. Okay, first thing was zip codes. What's the zip code for Kearney? 64060. Okay, zip codes have how many places? 1, 2, 3, 4, 5. So when we're talking about zip codes, we need to understand there's 5 positions for our zip codes. Okay, so how many possible zip codes are there? My first question for you is, what do zip codes contain? Zip codes are all what? Are they letters? No, they're all numbers. And how many numbers do we have? I'm going to write them over to the side. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what's after 9? 10. But technically, if I put a what at the very beginning, if I put a 0 at the very beginning, when I get to 10, I don't need to write it because 10 is made up of 1 and 0. So when I talk about numbers, I'm really talking about digits. How many digits do I have? 0 through 9 is 10. So when I talk about how many possible zip codes, blank, 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 5 blanks. Each of those blanks has 10 possibilities. So it's just 10 times 10 times 10 times 10 times 10, which gives you 100,000 different possibilities for zip codes. Now, changing that just a little bit, how many possible zip codes are there if 0 cannot be used for the first digit? So what's the only difference from what we did up here? There's still 10 possibilities, 10 digits for these, but 0 can't be in the first one. So instead of 10 possibilities for the first one, there's only 9 because 0 cannot be here. So there's only 9 possibilities for the first one, 10 for the other positions, which gives us a total of 90,000 possible zip codes where 0 cannot be at the beginning. Okay, let's look at the next one. If there are 5 students who can receive 5 different scholarships, how many different ways can the 5 scholarships be awarded? Well, there's 5 scholarships. 5 students can receive them. Here's my first question is, can one student receive all 5? Does it say anything about that? No, so one student could receive all 5. So when I think about these 5 scholarships and 5 kids for each of them, every kid has a chance to get every scholarship. So 5 students have a chance to receive all 5 scholarships. So it's 5 times 5 times 5 times 5 times 5, which gives me a possibility of 3,125 different ways that they're awarded. Now, if we change it a little bit to how many different ways can the scholarships be awarded if each student can only win 1? So how's that going to change this? How many people can win the first scholarship? 5 different people. But now, how many people can win this second scholarship? It's not going to be 5 anymore. There's only 4 because you can only have 1. So the person who won the first one can't win again. Okay, well after that one, this third one, how many people are going to be able to win that one? Then there's only going to be 3, and then the next one is just 2, and then the last one, that 5th person's going to win it. So 5 times 4 times 3 times 2 times 1, so there's only 120 different ways. Now, what we just did is called a factorial. That 5 times 4 times 3 times 2 times 1. Okay, this is called a factorial, where you take factorial is an exclamation point mark, and you multiply down. Okay, so 4 factorial would be 4 times 3 times 2 times 1. And if you type that in your calculator, you get 24. So what would 10 factorial be? 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 3,628,800. Okay, so this is our definition for a factorial. Okay, you multiply down. So on that last example, instead of multiplying all of those, we could have just done 5 factorial, and we would have gotten the same answer. Now, 1 factorial is just 1. Okay, obviously we can see that. 1 factorial is just 1. But now when I ask you 0 factorial, some of you are going to say 0, and I'm going to tell you that's not the right answer. Okay, so I'm going to tell you to use your calculator. Okay, these graphing calculators have factorials underneath them. Where do you think this exclamation point mark is going to come from? What is that menu that we keep using for almost everything that we do? Math. So go to math. And then the one difference is that I said we're doing chapter 10, which is all about probabilities. So what do you see under math? If you scroll over, option number 4 is PRB. What do you think PRB stands for? Probability. So scroll over to that PRB, and underneath PRB, you should see an exclamation point mark. That's your factorial. This is option number 4 under PRB. Okay, so math is that menu we keep using. Go to PRB for probability. Option 4 is that factorial. Okay, type in 0 factorial. 0, and then type in your factorial. Do you get 0? Okay, I'm going to give you a second to type it in. 0 factorial. What's your calculator give you? Not 0, it gives you 1. Okay, so that's one of those definitions that you need to make sure you remember. 1 factorial is just 1. 0 factorial is also 1. Now, Going a little bit further with this counting principle. The standard configuration of a New York license plate is 3 digits followed by 3 letters. How many different license plates are possible if digits and letters can be repeated? Okay, and that's a big part right here. Can be repeated. Okay, well, my first question for you. What's my options for letters? How many letters in the alphabet? 26. And then digits. We just talked about digits or numbers a second ago. How many digits or numbers do we have for possibilities? 10. So if I'm talking about a license plate, it says 3 digits, so I'm going to have 3 blanks for my numbers, followed by 3 blanks for my letters. And here's the key word. They can be repeated. So what's going to go inside of my 3 blanks for my digits? 10, 10, and 10. What's going to go in my 3 blanks for my letters? 26, 26, and 26. So my options are 10 digits times 10 digits times 10 digits, 26 letters times 26 letters times 26 letters. And again, fundamental counting principle, all we have to do is multiply them. There's 17,576,000 different possibilities. Now, changing it again just a little bit, how many different license plates are possible if digits and letters cannot be repeated? So same scenario, except now we cannot be repeated. So the first digit still has 10 options. But when I look at this second one, since we cannot be repeated, how many options do we have for this second one? There's just 9. Then how many options for that third one? It would just be 8. Then when we go to our letters, how many letters can be in my first position? 26. But then we can't repeat. So how many letters will be in that second position? 25. How many letters in that last position? 24. So we have 10 times 9 times 8 for my 3 digits, 26, 25, 24 for my 3 letters since we cannot repeat. You multiply them out. We went from 17 million possibilities down to 232,000. Okay, so we drastically went down just by saying we can't repeat. Now, the next kind of question we're going to talk about is permutations. You use permutations when you're ordering objects, and order makes a difference. So first place, second place, third place, something like that. First place is different than second place, so order matters. Okay? You're placing a certain number of objects within a certain number of positions, and it's noted by NPR. Okay, NPR. So, now this NPR stands for exactly what we just said. The number of objects and then the number of positions that you're filling. So N things placed in R positions. Now, if you were doing this by hand, here's how you would do it. NPR would equal N factorial, remember factorial is you're multiplying down, divided by N minus R factorial. Okay, and that's how we're going to do this first example is by hand, but then I'm going to show you a little shortcut. So our example, how many ways can you place 5 different students in 3 different chairs? So we have 5 for 3 positions. So it's 5 picking 3. And that's kind of how I say this. 5, I'm picking 3. So if I'm doing this by hand, how would we do this up here? N factorial, so that would be what? What's my N? 5. N minus R would be 5 minus 3. And this is 5 minus 3 down here. What is 5 minus 3? 2. So this is 5 factorial over 2 factorial. I'll write it out for you since it's cutting off on the screen. 5 factorial over 2 factorial. Well, what is 5 factorial? 5 times 4 times 3 times 2 times 1 over 2 factorial is just 2 times 1. Now, what have we said about division? When we have straight multiplication, we can cancel things. What can I cancel? I've got a 2 on the top, a 2 on the bottom, a 1 on the top, a 1 on the bottom. So the only thing I'm left with is this 5 times 4 times 3. And that's going to happen when you do your permutations. Okay, those commons are going to cancel, leaving you with what you have left, 5 times 4 times 3. So for this example, 5 times 4 times 3 is all we have left, which gives us an answer of 60 combinations or permutations. Now, you can use your calculator. Okay, first question, what option do you think it's under? Math. And then same as before, what are we talking about? Probability. So you have to go over to PRB. And then do you see an NCR, or I'm sorry, an NPR? It's option what? This is option number 2. Okay, so we're going to use our calculator to actually do this formula for us. Okay, so let's look at our next example. There are 8 different people running in the finals of the 400-meter dash. How many different ways can they place first, second, and third? 8 people picking how many positions? First, second, and third. So I have 8 people, and I'm picking 3 positions. How do they get first, second, and third? And how do I know it's a permutation? Because order matters. First, second, and third, there's a big difference. Okay, so if you haven't yet, type this in your calculator, 8, and then do your NPR, and then do your 3. There's 336 options. Now, some of you, it might make more sense in your head to do this in a little bit different way, which is fine. Okay, if I made this in a sense of just blanks, how many people can get first? How many people can get second? How many people can get third? How would you figure that out? If I just did the counting principle, how many people can get first? 8 people. How many people can get second? 7. How many people can get third? 6. And if you type 8 times 7 times 6 in your calculator, you will also get 336. Now the next one, in how many ways can a batting order be made from a team of 17 softball players? Okay, well, first thing, I have a total of 17 players, and I need to pick the batting order. Okay, well, those of us who know anything about baseball or softball, how many people bat? How many positions? 9 positions. So how am I going to fill this in? I have how many, and I'm picking how many. I have 17, and I'm picking the 9 who bat. So 17, pick 9. And those of you who wonder why baseball and softball coaches have a hard time picking batting orders, there's 17 kids. There are 8 billion different ways, 8.8 billion different ways to pick that batting order. Okay, that coach has a lot of possibilities. Now, doing this just with placements, there's 9 positions, so I could do what? Put out 9 blanks. How many people could go in the first one? 17. How many people could go in the next one? 16. The next one? 15. The next one? 14. 13, 12, 11, 10, 9. And then guess what? If you multiplied out those 9 positions, you would get the same answer. Next one. How many possible ways can 3 cards be drawn from a deck without replacing them? Again, that's a key word, without, so you keep them. Okay, so how many do I have? A deck has what? A deck has 52 cards, and I'm picking how many? 3. 52 pick 3 gives me 132,600 choices. And again, if I just wrote it out as a counting principle, what would I get? How many can I pick the first time? 52. The second time, 51. And the last card, there's 50 choices. So if I figured out my choices that way, I'd get the same answer. Okay, and the next one, almost done. 6 runners are in the first heat of the 100-meter sprint. And how many different ways can they end? Okay, well, how many people can end first? 6. How many people will end next? 5. And then 4, and then 3, and then 2, and then 1. So there's 720 different ways. What's another way you could have typed this one in your calculator? Okay, there's actually two other ways. I could have typed what factorial? 6 factorial would have given me the same answer. Or if I did permutations, I have 6 runners. How can all 6 of them end the race? I could have done 6P6. 6 runners, 6 finishers. Okay, and any of them would have given me that answer. How many ways can the first 3 spots be filled? Spot 1, how many people can fill spot 1? 6. How many people can fill spot 2? 5. How many people can fill spot 3? 4. So just those first 3 positions is 6 times 5 times 4. So there's 120 ways to fill those first 3 positions. What's another way you could have done this? You have 6 runners, but in this question, you're only picking how many? 6, pick 3. Now, last part. How many distinguishable permutations of the letters are there in math? There's 4 letters, and how many different letters? I have 4 letters, and I'm picking how many of those letters? 4. So this is just 4, pick 4. There's 4 letters, none of them are repeated. So 4 pick 4 is 24 different permutations. Now this is going to change if the letters are repeated. If their letters are repeated, you have to divide by those repeats. Okay, so whatever those repeats are, you have to divide by. Okay, so let's look at another example. Basketball. 10 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 letters. But I said I have to divide by the repeats. Well, what are my repeats? A and A, L and L, B and B. Do I have any more? S-K-E-T? No, so I have to divide by those repeats. I have 2 B's, 2 A's, and 2 L's. So I have 10 factorial on top, dividing by my repeats, 2 factorial times 2 factorial times 2 factorial. And if you're using your calculator, make sure you have parentheses. If you don't have parentheses, you will not get it right. So 10 factorial divided by 2 factorial times 2 factorial times 2 factorial equals 453,600 different permutations. Okay, the last one, Mississippi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. 1, 2, 3, 4 I's, 2 P's, and 4 S's. So are we going to write this? What's our total on top? 11. Our repeats, I've got 4 I's, 4 S's, 2 P's. So 4 factorial times 4 factorial times 2 factorial. Again, you have to have parentheses. And there's 34,650 different options. So I hope you enjoyed beginning probability today. We'll get a little bit deeper in the next coming lessons. Here's your homework.